me great pleasure actually to introduce our next speaker, who's going to deliver something special. It's the memorial lecture for John Hunt, a stalwart, past stalwart within our own solidification field. I introduced Professor Lorenz Ratke, who received his John Hunt Medal in December of last year. Former head of department of materials at the German Aerospace Center, DLR in Cologne, in Germany. Another awards collector. This one specifically, I like this one for innovation, picking up innovation awards both in the city of Cologne and the Bavarian state. So without further ado, Lorenz, will you deliver the John Hunt Memorial?
Yeah, I do. Okay. Yeah, you switch it. Okay. So, good afternoon. I would like to take you on a journey or a time travel. So it's possible in principle. I just read it in a newspaper. At least in some quantum states, time is reversible. Okay, and I would like to start some. Okay. Oh yeah, that's fine. So I would like to start with my lecture in the mid-80s and hopefully today somewhere. And I would like to convince you or persuade you that between immiscible alloys, so metallic materials, and aerogels, an example here is resorcinol formaldehyde, there are close links. And one of the links is, of course, the phase diagram, so thermodynamics, which is important, but it's also quite different from metallic alloys. So, I should do it this way. So, immiscibility, I wouldn't do this. Yeah. Immiscibility is, as you know as a material scientist, a quite general phenomenon. If we would only have alloys or components or elements which are always miscible, what a nightmare. Because miscibility in the solid state or in the liquid state makes a lot of wonderful microstructures. And it's essentially due in the most simple model, that's a regular solution model, ideal entropy of solution, and of course a mixing enthalpy. And the important point is that the mixing enthalpy is positive. Then you see in the free energy diagram that exactly a miscibility gap appears. This is very simple, like atoms, like each other more than different components. The point is, in reality, it's in metals you always see a miscibility gap with an upper critical point. I do not know of any example which has the opposite. But in organics, you have also systems with a lower critical point, and I'll show you later an example of that. This is due to that this enthalpy of mixing depends, for instance, on temperature. And in reality, of course, everything is not that simple. In reality, the ideal entropy of mixing might be dependent of much more complex terms in concentration. And the enthalpy of mixing has not this simple parabolic form, but has additional composition dependence here. And let me say a remark, even in organic materials, you might have a closed loop. So this miscibility gap is in the temperature composition range really close. It depends on how the molecules interact with each other. So let me come first to, and this is the time travel, go to liquid immiscibility. And I was concerned with liquid immiscible alloys for quite a long time, thinking about in combustion engines, so this old stuff where we heard this morning in 20 years, so that's beyond my expectation value. We all drive electrically, but in combustion engine, these immiscible alloys was thought to be wonderful self-lubricating bearings. So people were interested in aluminum, lead, aluminum, indium, and you see typical phase diagrams. You have a critical point, you have a miscibility gap in the liquid state, and the difference between critical temperature and monotactic temperature is a few hundred Kelvin. And there are a lot of these binary phase materials which show a liquid miscibility gap. Wonderful, let me say this, iron silver, silver nickel is an exception from all this, because in these materials, you find, if you looked into the phase diagrams, not even a critical point. They are completely immiscible in the solid and in the liquid state, and such a diagram would look like you have the melting point of, let's say, silver, the melting point of iron or nickel above, and that's it. And even from these materials you can make really important materials in daily life. By powder metallurgical methods, you make power switches, which are important for all these what is that? Power switching electrical lines. But there are also metastable miscibility gaps. For instance, copper cobalt, copper iron, there are metastable miscibility gaps. How to reach that? Here you would simply do deep undercooling of these melts. You melt such a material, let's say in an electromagnetic levitation facility, do that in vacuum or in inert gas, cool it, and if you do it nice, and Dieter Herrlach did a lot of research on that, and his co-workers still do a lot of research on that, and you are able to suppress the crystallization of, let's say, cobalt, and you can go directly into the miscibility gap, and so you see a wonderful two-phase structure. Important, and it was mentioned this morning, that iron slags are also immiscible. So, for instance, if you deoxidize iron with silica or with silicium, iron-silicon mixtures, then you form silicon oxide, and silicon oxide is in an iron melt liquid. So I have a liquid phase in a liquid matrix. So I should do that. So let me come to the important point of phase separation. So the bad thing is, if you have such a liquid miscibility gap, the bad thing is between the critical point here and the monotactic reaction temperature. I'm not talking about this monotactic reaction because it's very similar to a eutectic with one essential difference. One of the phases is liquid. So you have a liquid-liquid interface, and in a gradient, this will induce interfacial convection and change the microstructure and change the well-known relations derived by Jackson Hunt and by Tiller for eutectics. I'm not going to talk about that. Here is a real difficulty. If you have such an alloy, you cool through a miscibility gap. As I've written here, you have typical intervals for slightly hypermonotactic alloys up to a few hundred Kelvin. So whatever you do, if it's not rapid cooling, typical cooling rates in directional solidification, there's ample time for, once you go below the binodal line, the second phase appears either by homogeneous or heterogeneous nucleation. They will grow, and if they grow in a supersaturated matrix, either by diffusion or convective diffusion, this liquid phase here has a possibility to do Stokes motion because it's in aluminum. Let's think of that. It's much heavier, higher densities than the aluminum matrix, so it will follow gravity and sink down to a sample. Or you have, of course, because there's liquid interfacial tension, you have either consoluble or thermal Marangoni motions. The droplets move from the cold area in your sample to the hot area and dissolve there, of course. And then, of course, in as much as these droplets are there and they move around, they can collide. And if they collide, they become bigger. I show them move in a few seconds. They collide, become bigger, settle in a gravity field again. So collision and coagulations you have to take into account. And a way to do that, I will show you an example of that, is population dynamics. And of course, at the end, there's a monotactic reaction front, and they will interact with this monotactic reaction front, disturb this front, of course, maybe make nucleons for new phases there. This has to be taken into account. And of course, there will always be, due to density difference or temperature gradients, the possibility of having natural convection. I'll also show you a modeling of this natural convection. And coming to a few points, as I said, this temperature interval is typically around 100 to 300 Kelvin. Cooling rates are, in a typical directional solidification experiment, 1 Kelvin per second up to maybe 100 Kelvin per second. So it takes around 10, 20, 30, 40 seconds that the droplets which appear have time to do some motion and to produce some microstructure. You see in the end in a solidified sample a microstructure, and you have to reconstruct with all the possibilities here, how did this microstructure really realize? That's complicated. The length of this this two-phase zone is of the order of few millimeters, 10 to 30 millimeters, depending on the temperature gradient. And the time in the miscibility gap, as I said, is around a few hundred seconds. Diffusion rate in liquid is fortunately fast enough, so it's 10 to the minus 9 square meters per second. So diffusion and growth by that occurs rapidly compared to, let's say, a solid state. So I will show you the movie made by Ranvald Matthijssen. Yeah, it works. Ranvald Matthijssen, Lars Arnberg, and Paul Schaffer, they made it with at the beamline in Grenoble. And you see here, cooling an aluminum bismuth sample, we had a joint project on that. And you see here that the droplets appear in front of the monotactic reaction front. They move a lot, move upwards, which is Marangoni motion. And you later see, yeah, a few, if they collide, I show it later here, if they collide, yep, they go down, and everything which goes up dissolves, because it's hotter there, the solubility is better. Think of the shape of the miscibility gap, that's it. And I've looked to all these movies many times, and I have to say, thanks to these colleagues doing this, because this is the first time that it was ever done in these hypermonotactic alloys that people really looked with X-rays into the real processing occurring. And it was, for me, a lot to discover. This is simply wonderful what they did there. So here, just showing you the collisions here, which occur here. And if the droplets become large enough, they really settle. And this is another movie showing exactly that. If they collide, they really are big enough so that they fall down. And this is due to the fact that Stokes motion goes proportional to the square of the radius of a particle or a droplet. Marangoni motion is linear. So if you have a linear velocity as a function of radius, linear, the other is parabolic. If the droplets are small enough, Marangoni wins. If the droplets are too big, Stokes wins. That's very simple. Okay, so start with all these processes. The idea is the processes, once you cool below the binaural line, there must be some nucleation, or the droplets must appear somehow on stage. How do they do that? There's a very old paper, very old, well, okay, 1982, yeah, that's 40 years old, made by John Perepetsko and his co-workers, and they measured in gallium bismuth under cooling with DTA, which is not so easy to do because the phase separation, once it occurs, or the nucleation of these droplets, makes only a small thermal event. So you must have a DTR with a high resolution in enthalpy. This is possible. We built our own DTA at that time, not a commercial one. We built it just to have to measure a very small thermal event. And here they could show that in gallium bismuth, that's here the miscibility gap, and on the side of gallium, there's almost no undercooling, but on the side of bismuth, there's a huge undercooling, a few 10 degrees Kelvin. And we measured the same with zinc lead, and we could show, yes, the droplets appear with an undercooling 10 to 50 Kelvin, and Laszlo Granashi was at that time at DLR, and he said, well, I can model that. I take the model of a homogeneous nucleation, and I calculate that, and this is my calculation. So we had the idea, well, that's homogeneous nucleation. I know whenever I presented that at any conference later, there was no one in the audience saying to me, wonderful that you measured that, but I do not believe it. This is nonsense. There is no homogeneous nucleation. I guess they were right. So, because we made later some wonderful experiments with aluminum lead and added some grain refiners, titanium diboride particles, or a classical grain refiner alloy. Did X-ray tomography, and you simply look to this here. This is an X-ray tomograph without any grain refinance that. Now we added titanium boride particles, same, everything's the same cooling rate, same sample size, etc. All other parameters the same, and you make X-ray tomography from that, and from here to here you nicely see these are much more particles. So it's definitively something like heterogeneous nucleation. We later looked into that much more detail and could show for, especially in the papers with Ivan Kaban, he was at that time in Chemnitz, now he's in Dresden, that he measured the wetting angle of the lead-rich phase to a plate of titanium boride and could show, well, the wetting angle is very small, so it's the catalytic factor you calculate is also very small. Well, it's heterogeneous nucleation. Don't worry, our conclusion we have drawn years ago is simply not correct. Okay. That's okay. Then the other point is, and that's also part of the time travel, when Skylab was flown in the late 70s, people, of course, made experiments with immiscible alloys. And I thought, well, we get rid of gravity. And if we get rid of gravity, we will get a wonderful dispersion of droplets in a matrix, solidifies it, and then we have a super material for bearings. Well, they come back to Earth and said it's the same massive phase separation and segregation as on Earth. What is the origin? And it was shortly after that discovered, it's this Marangoni motion discovered in the mid-19th century by an Italian physicist. And this is due to the fact really that the interfacial tension depends on temperature and depends on concentration. So let's only take temperature, and if you have a droplet, on the top it's hot, here it's cold, then you induce simply a fluid motion at the interface, leading to the point that the whole droplet moves from the cold to the hot side, and the rest of the fluid goes just in the opposite direction. As I said, linear with radius. So we again thought, okay, we would like to improve that. And how can you do that? One of the ways you can do, fortunately enough, you have not to wait for Space Lab every 5 to 10 years in an experiment. So it's far beyond the time scale of a PhD student. So we said, well, in a PhD student of one of my students, we said we take parabolic flights. How to make a casting in a parabolic flight. And in parabolic flight, you should say the plane is up to around 7.5 kilometers in height. It's 1g, then it enters up in a 2g phase, and then it flies a free fall parabola for around 20 seconds, something like that, 10 to the minus 2g, something like that, and then it comes back, and you do that 30, 40, 50 times again. So one calls it vomit bomber. In a certain sense, this is not incorrect. And how do you do then a casting? Very simple. We take a furnace, cast on Earth the alloy in there. Then in space, so if we are here in this phase, you heat it up, have a stirrer there in, because immiscible alloys, you cannot wait until diffusion does the mixing. So you stir it. We have stirrers there in, and then in exactly this phase, you turn this facility upside down so that the melt goes by itself with 2 times gravity into this aerogel mode. It's a silica aerogel mode made out of silica aerogel, because the silica aerogel has a thermal conductivity of 20 milliwatt per meter Kelvin. So it's almost none of thermal conductivity. So it isolates perfectly. Then it sits here in, and once the microgravity period comes in, you have an indium bismuth alloy and a piston, and bring it here to this small sandwich foil and cool it from the bottom. And if you do everything nicely, you see for all the alloys we investigated, you have something like solidification velocity of 1.5 millimeter per second. Cooling rate varies, of course. This is measured optically. We have an infrared camera. You measure at the surface temperature, and you can say, yeah, but the interior will be different. No, due to the fact that aerogels have a very low thermal conductivity. You just have radiation heat losses. You can wonderfully measure that, and you can, by numerical simulation only, show that the isotherm is almost flat. So it has a bending of maybe 20 microns. That's it. So we have cooling rates in the 50 to 100 to 50 Kelvin. And what you observe is exactly then what you would have expected. Under gravity, the lead is at the bottom. Under in microgravity, all the lead is at the top, as it should be. We did it hundreds of samples. So my students who went to Bordeaux to do this for a fortnight were there and enjoyed being there in a wonderful house at the beach. They enjoyed it. I never did that because I thought of this vomit bomber. And but my student enjoyed that. And they made a lot of experiments, and then we, of course, evaluated it carefully. And you can make very simple models by just say it's nucleation, it's diffusion, and Stokes and Marangoni motion. You neglect coagulation, and you can say, well, somehow it fits more or less. Not really good, but for an analytical model, it's okay. We will later see why it's not that good. Oh, I'm too fast. So we did modeling. What you think about then modeling is everything depends on everything. So because you have a lot of processes, how to do that? We said first, for this alloy, at that time in a bigger project, the group of Bruno Predel and Ferdinand Sommer in Stuttgart really measured all the thermodynamic quantities of aluminum lead and aluminum bismuth. This was very important. So we had the full thermodynamics with that optimized phase diagrams. So, and assuming it's homogeneous nucleation, at that time we thought it is that, then you can, of course, say, well, you have a cooling, you have a prescribed temperature field, you have a nucleation event. Then if there's nucleation event, you have to take into account that the drops move, so have mobile sources of temperature and solute, not to forget that. The mobile sources, of course, do in parallel diffusional growth. You could do coarsening in principle. So if you do that numerically, you can also calculate Oswald ripening. Although I would say it's too slow. But nevertheless, you put that into the equations. This changes, of course, all the temperature, the concentration field, the Marangoni and Stokes motion. To take that into account, you have to have a good model how to describe coagulation. And let me make a simple example. If you drive in winter through falling snow, you will note that not every snow flake hits the windscreen. A lot of them just pass by. There are enough hitting the windscreen. But a lot flow by. And this is due to hydrodynamic or, in case of snowflake, aerodynamic interactions. So you have to calculate, if you would like to do this correctly, you have to calculate the flow rate around the droplets, either doing Stokes motion or Marangoni motion. Fortunately, a Russian scientist did it at the end of the 80s, reinvented by Bob Davis from Boulder in the mid-90s. They calculated the full hydrodynamic interaction of droplets. So we put that you put that into all these numerical codes, and we were able at that time. Today, I think you could do it better, to track really the path of 40,000 droplets in a given volume, what they do, the temperature field, the concentration field, the coagulation events, etc., etc. Today, I think with modern computing facilities, it would be easy to calculate for 40 million. Okay, so this is temperature field the same we did in parabolic flights with aerogels we did in the lab. So we knew exactly when we started solidification, and we did it unidirectional in an aerogel cylinder. And you see, it takes some time, if you follow this by infrared cameras, some time before the solidification front really is through the whole sample of 20 millimeter length. So then you have nucleation event, only here one recorded. It can repeat in as much as the solidification front proceeds. There can be one nucleation event, it proceeds a few millimeter, a second nucleation event, etc., etc. It's a complex interaction of concentration fields, decreasing supersaturation, drops move, increasing supersaturation. It's really complicated. So you can have periodic nucleation of droplets. But nevertheless, we were lucky that the measured bismuth concentration and the simulated one agree very well, and for the droplets stemming from the phase separation, not from the monotactic reaction. You have deconvolute the particle size distribution. If you deconvolute it and say these are only what is left over from the phase separation in the miscibility gap, the calculated sphere radii and the measured sphere radii agree very well. So, sounds good. I think it's not good enough. The other point is, and here's the first connection with aerogels. The other wonderful idea came up at that time is we start with a wonderful equation derived 1916 by Smoluchowski. And he did that to describe Brownian motion. This was his essential idea. I would like to describe Brownian motion. He did that in this way, not in this continuous way, with continuous size distribution, but with discrete size distribution, and all the particles had the same size. Well, this is the first link, because if you think about this, in the 80s and 90s, what came up, one of the hypes was fractal structures, diffusion-limited aggregation, diffusion-limited cluster aggregation, reaction-limited cluster aggregation, and this, all the mean field for a theory for that is exactly this equation. And cluster aggregation is exactly that, what is one of the models to describe the formation of aerogel structures. So see, when I years later came into the business of aerogels, I thought, beautiful, what a luck. You can use the same mathematics as you did it for immiscible alloys, by accident. So here it's a burst rate, there's a collision volume, which is essentially scattering cross-section times the relative velocity. So they have different velocities here. And if they would be on straight lines, this would just collide. If you do such an experiment at home, you just take an oil, whatever you have in the kitchen, take water, have a pipette, and look that you have one droplet there, take with a pipette a second droplet, and try to coagulate them. You will find out it's not that easy to do that. So this is really, interaction is very complicated. I did that. So to your point this morning, you have to do by your own experiments, an observation and making discoveries. Okay. So then, of course, this is, of course, not how do you describe the complex phenomenon in immiscible alloys. You add a nucleation term on the right side, you add a growth term on the left side, you can add, but need not, adding Ostwald driving droplet motion also on the left side, which makes it then space dependent. So it's another variable. And of course, you have to have some definition of collision volume, which is difficult. Let me say this equation is also the basis of cloud dynamics. There was a nice book published in mid-90s, Cambridge University Press, entitled Cloud Dynamics. When I read that, I saw first these guys doing cloud dynamics to study rain formation, drop in clouds. They solved all the problems I also solved. And I said, well, okay, I should have read the literature. But this is one of the bases. Aerosol mechanics is exactly the same. So, okay, and if you go further, you add conservation equations for heat, for mass and species. And if you are interested in this, then a wonderful review written by Jitsu Zhao and Ji He in Acta Metallurgica Sinica, and a recent review where this and the extended version of this model is really very well described, and all complications you can do in there. And one of these issues, Jitsu Zhao, when he was as a Humboldt fellow in my lab, was exactly studying this. You take an aerogel crucible, cool it from one side, you have no radiation heat losses in radial and axial direction. You calculate the temperature profile compared with experimental ones, of course. And finally, depending on the cooling rate prescribed here, you have different lead concentrations in aluminum lead sample. At the bottom you have a layer, as you observed it in experiments. And then if you increase the cooling rate, Marangoni motion becomes more prominent because that's proportional to the cooling rate. And if you do it fast enough, you have really indeed, you can shift, even in gravity, you can shift a lot of droplets to the hot side of the sample. So, that's not the end of the story. because we simply then think, when we had this project where also Lars Arnberg and Reinhard Mattison were in, we had a nice joint project because with two companies together we would like to develop indeed aluminum lead or aluminum bismuth better bearings. And Meng Huai Wu and Andreas Ludwig said, well, we can model that. And what they did is, of course, they used the multi-phase volume averaging model, which is in principle goes back to Viscanta and Christoph Beckermann in the 90s. They edited this with mobile heat and solute sources or sinks, additional terms for Stokes and Marangoni motion, and of course describe coagulation of drops by either Brownian motion or by shear collisions. And of course you put in a nucleation model going back to Rapa as far as I mentioned. And the fine thing is, I like this movie very much. You see cooling it from the bottom. Here is the cooling. You directly start with the cooling. You see that a lot of droplets appear. And since here the cooling also starts later at the top, and this would be the final microstructure. And we could compare that with experiments. It generally is not that bad. The point is, well, yeah, okay. In the 90s, it came up, end of 90s for us. Isn't it possible to use phase shift model and combine it with convection? Up to that time, people studied with phase shift model, dendritic solidification, etc. But convection was a difficulty. And we did that with Adam Wheeler and Britta Nessler, now at Karlsruhe Institute of Technology. And we combined Kahn-Hilliard equation with Navier-Stokes equation, and taking into account, however, that explicitly you can include interface-driven convection. You had to do extensive stress tensor in the Navier-Stokes equation. One of the results of Britta was that indeed what you observe here is that in front of a monotactic reaction front, the droplets can coagulate, and they can even interact with the monotactic reaction front and perturb it so that it's not a planar interface. This is an artificial monotactic, and it's an artificial phase diagram, because typically in monotactic reactions, the liquid phase has a volume content of around 1 to 3-4%, but not this extent as here. Much better was. Does it run? Yeah. What was done by Laszlo Granashetti and Jörgi Texe. They simulated an aluminum artificial phase diagram of aluminum bismuth and put their sample just below the spinodal, so that you need not to take into account how does nucleation work. Because in the spinodal, concentration fluctuations do everything by itself. They amplify by themselves. And what you nicely could see is that the droplets, in as much as they come closer, they interact. This is the way the interaction of hydrodynamics in reality works. This is wonderful. So it's really doing at the end a big blob. So let me come to the other point. Aerogels. What do they have to do with immiscibility gap? So before I do that, I would like to introduce to you aerogels, because I'm not sure if everyone knows what an aerogel is. So if I'm taking oaths to Athene, okay, forgive me. Aerogels are open nano to mesoporous structure, open porous solids, always open porous, and they're typically, this is an example, I do not know, all made via a Sol-gel technology. All. You can make aerogels from anything that gels. Most famous are, of course, silica, but titania, zirconia, mixed oxide, silicon oxycarbide, silicon carbide, everything is possible. Polymers, of course, resacylone formaldehyde, polyimides, polyurethanes. You can, from these sources, always carbonize them to get carbon aerogels. You can use biopolymers, cellulose, gelatin, egg white, agarose, and recently, 5 to 10 years ago, Eichmüller in Dresden made a lot of metallic aerogels out of almost all metals. You just need to have a metal salt, and you can transform this into an aerogel. So in open porous structures like this here. This is resveratrol formaldehyde, nicely spherical particle. Size is typically around a micrometer, but typical for aerogels is this is resveratrol formaldehyde. It looks like a Hollywood spiderweb in nano size. That's it. And if you do that with cellulose, you have also a wonderful spider web. These are really then nanofibrils, 10 to 20 nanometers in diameter. Here, if you look much closer to this, which is not easy because these ugly polymers have no electrical conductivity. So to do that in scanning electron micrographs is not that nice. But it works. You see these are in reality small strings of pearls. Hey. Yeah. So now you see how one really does it. That's a real experiment in real time. So one of my postdocs mixed resveratrol in water solution and added then formaldehyde with a catalyst therein. Shakes it a little bit. You see a lot of whatever appears, particles. It was clear, now it's turbid, and now it's got piggy pink, and it's gelled already. This is real time, but typically gel time in aerogels is hours, 2 days. So, but this is fast. So what we have at the end is you have a network of particles, however they aggregated, and you have just to remove the liquid, and you get out of that an aerogel. Okay, classical idea. Therefore, I said that was my first link to immiscible alloys is, you dissolve all the monomers or what you call precursors. You have somehow an hydrolysis for silica activation and polycondensation reaction. So somehow particles are formed. They aggregate by whatever mechanism to a spanning network. So it's a wonderful idea of percolation, spanning clusters, branched networks, etc. And if you have that, you just remove somehow the liquid and that's it. And if you do that carefully, you can preserve, hopefully, the solid structure in there. So, few illustrations of this model. This goes back to a wonderful book of Ralph Ehler on silica itself, silica gels. And it said if you do it in acidic conditions, working with silica, you get a fractal network. If you do it under base conditions, you got more bigger particles used to study, for instance, colloid crystals. And this is the same done a few years later with this resveratrol, which is a dihydroxybenzene. You have two OH groups with formaldehyde. They react, build methylene bridge or methylene ether bridges, make a gel network, and that's it. And hopefully this runs now. Here's a wonderful DLCR simulation done by Bill Halperin from Northwestern University with different particle sizes, and he just said, well, depending on the mass, they can make Brownian motion, and they made at the end a spanning cluster. Wonderful. But for me personally, the wonderful thing is with this, there was still, going back to the mid-90s, the idea, maybe what we think about this cluster aggregation, this Brownian motion, maybe this is completely nonsense. It's phase separation. If this phase separation, how to understand that? Cedric Gomez from Liège looked into that and said, well, either it's a kind of phase separation or spinodal decomposition. It's difficult to discriminate from the, let's say, small angle X-ray scattering. In cellulose aerogels, Falk Niebner from Vienna and Tatiana Butova from Sofia Antipolis said, well, whatever a microphase separation is, but that's what the chemists say to that. Well, it might be a responsible structure for motion in cellulose aerogels. So an answer might be time-dependent miscibility gaps. You can say time-dependent. This is nonsense. Because thermodynamics is equilibrium. Time is not a parameter in thermodynamics. But what happens if a miscibility gap develops due to chemical reactions? Could that be a key to understand gelation? Well, when we had this idea, together with colleagues from KIT in Karlsruhe, we thought, okay, how do you describe that? Classical description of in polymer science is the Flory-Huygens theory. They don't call it regular solution. But if you look to this, say degree of polymerization 1, then it's exactly regular solution model. But the point is, the degree of polymerization changes the entropy of mixing. So that a phase separation on the free energy diagram to minima appear is due to that if the degree of polymerization increases, there are less possibilities to arrange the long chain molecules. So this is exactly what happens here, and that's the model made in the 40s or 50s by Paul Flory and one of his postdocs, Huygens. That's wonderful, and indeed in a lot of polymeric systems you can really observe porous structures even in the nanoscale, depending on the polymer and of course on the solvent used there. So and see this, the degree of polymerization is linear in time. This is not an estimate, not something, this is exact. If you calculate polycondensation, you really find out that the degree of polymerization always increases linear with time, and not with a cube root, a square root, or whatever, or power of sound is exactly linear in time. If you do not believe, I can show you how to calculate that. This is to calculate that, go back to Smoluchowski's equation. This shows you exactly that. Or take Caruso's law, which says if you have a chemical reaction, the amount of material reacted defines the degree of polymerization. This is exactly the same. So the point is, we just made studies with an upper critical point, a lower critical point, just assuming that the Flory-Huygens parameter or the entropy of mixing is linear in temperature. I know that this is only a model. It has nothing to do with reality. The bad issue is here. I can only say that no one knows the thermodynamics. So that's a play field for theoreticians. Something, I would say it's a challenge for experimenters to really measure thermodynamic quantities. You will not get a Nobel Prize for that. And not have the super material, but you did something good for the science community. So, and the point here is what you can see here. If you would initially have a concentration here, initially everything is miscible. In as much as the degree of polymerization goes from 1 to 720, then the points move into the spindle. Here only we plotted the spindle, that's a binodal here. So, since it's time dependent, a state point runs in from a single phase field in a two-phase field. So, and then there should everything happen, what we know from immiscible alloys. So, what we do is just say, well, of course, what we did is, with the colleagues in Karlsruhe, phase field modeling, what else? With convection, that's it. And you have to take that into account, and that's it. So don't be worried about these equations. It's just to say, the only important point is this term here. You combine it with the Navier-Stokes equation, you have an advective term here, the rest is standard. You read in textbooks on Canelian equation. Stokes equation is up to, besides this point, here is the standard full-scale Stokes, Navier-Stokes equation, and you have to add an additional term to describe interfacial-driven convection. And we calculated these numbers, this capillary number here for Rosacino formulate. It's around 300, so there will be an effect. First, what you do is, of course, doing 2D simulations, and then start with 10, so just inside the spinodal, and you see from concentration fluctuation that particle droplets appear. And if you have capillary flow, instead of being regular arranged, they are irregular arranged, looks similar to monotactic alloys. And this is just to show that the droplets coming closer, they have interaction of the fluid phase fields, the solute fields. This is well known since 1959 or something like that. made by Golovin, who made a wonderful calculation of two droplets coming close to each other, and if they come close to each other, there's a different solute between them along the center line than outside. This gives rise to solute Marangoni motion, and the droplets coagulate. This is since that time called Tanaka-Golovin mechanism, because Tanaka later derived it in the mid-2005, something like that, in a much more better way. So, we now go to this system with exactly different volume contents, this point, this point, this point, as a function of time. So we have the degree of polymerization varying and different capillary numbers. And what you see here is what I mentioned. You see exactly a low volume fraction which would mimic monotactic, slightly hypermonotactic alloys. You see at the end with larger capillary numbers, this looks exactly as our 3D tomography of a rapidly quenched immiscible alloy. There's not a big difference. If you increase the volume fraction, of course, then the droplets interact much more, and finally they would make a big blob. Well, that's not interesting. And I skip that. And the point is, how to now to describe gelation. The point is, or the essential point is, yes, once the liquid miscibility gap evolves and crosses a state point, then a second phase, polymer-rich phase, liquid phase, appears as a droplet. But the polymer concentration is that large that these polymers do a very simple thing. They do a percolation transition. Because you typically, if you look into the literature on percolation, look to the book of Aharoni and Stauffer, or there's wonderful websites on percolation available. Then it says always, if it's something like beyond volume fraction of polymers here, larger than 40-50%, they will directly make a percolation transition, and then this is a wet gel particle, no longer liquid, not really solid. It's a mixture between liquid and solid, and of course, because it's also here liquid, there are oligomers or even monomers therein, so there would be interfacial tension-driven flow possible. And so this would then have the ability to connect to each other and make a string of pearl network and making a spreading cluster. And we are currently, this is work in progress, we are currently trying to describe this without, so of course, as a simple material scientist, I said to my colleagues in Karlsruhe, well, that's a computer program, put a switch in that, say 1 degree below the miscibility gap, make a switch, now you are a solid particle. And we can study at least, let's take a look if this gives a network. And of course the colleague said, no, we are not cheating physics. We would like to understand the viscoelastic behavior. And of course they are right. I would try to convince my PhD students just to look what happens. If we are on the right track or on the wrong track. This might be at the end you make such a big simulation. These simulations run all on more than 10,000 parallel CPUs. So you waste a lot of money if you do not know if you're on the right track. So why doing that? Well, okay. I think they are right. Because we found out recently, we have published a paper on that Brownian motion of droplets is different from Brownian motion of solid particles. Brownian motion of droplets can really make straight lines and not zigzag lines, depending on some physical parameters. And this would make a transition from diffusion limited aggregation to reaction limited aggregation, just due to the fact that the droplets are not, the particles are not solid but liquids. So, okay. So, some experimental hint why I think this is phase separation. This is an estimated phase diagram of zinc chloride trihydrate with cellulose. That is a solvent for cellulose. And if you do an experiment, so you go in a viscosimeter, you heat it up, so let's say to 90 degrees, cool the solution down, you find it gels at around 40 degrees centigrade. You heat it up again, you dissolve everything, and you cool it up, you find again it dissolves, it gels at 40 degrees. So it's reversible. cellulose seems to be a reversible system with an upper critical point. The same you would find also when you do not do salt hydrates, but methyl morpholine oxide, which is also a wonderful solvent for cellulose. Okay. In resacino formaldehyde, the Cedric Gomez measured critical opalescence. So this is a hint to colloidal formation. If you remember, critical opalescence is a well-known phenomenon observed, I forgot that, 100 years ago. So where you really see a transparent material becomes certainly at a certain temperature, it becomes turbid. And you measure the scattering, light scattering, in this case you X-ray scattering, measured this critical opalescence, showing this could be formation of colloidal droplets as we had it. And said, well, now they must become wet gel droplets and then do everything else. So for small X-ray scattering, there's a wonderful measurements made by Horikawa. Say initially everything is just scattering and has nothing to do with colloids. And if time goes up and it becomes a gel, you see a Ginye shoulder and you see a Poirot regime. So from here to here is a transition to describe the gel formation. And ultimately, I have to say, Cedric Gomez did a nice job as he, from the Sachs curves, reconstructed with Gaussian random waves how the structure could look like. For different, these are only different catalyst concentrations. And it comes somehow close to reality. So, summary is, the schematic picture for polymer systems would be solutions of monomers, polycondensation or polyaddition to oligomers or chimers. You have formation of pre-nucleation clusters because there is no need for heterogeneous or homogeneous solution. You have already a lot of polymers with different degrees of polymerization in the systems. So once the binary touches the concentration of the polymers, phase separation sets in, probably on these pre-nucleation clusters, and there is, depending on where the concentration, you might have spinel decompositions, this was observed, and or aggregation to a network. If you look for alloys, that's the same, solution of atoms. I come to this in a second. The temperature drops below the binary, you have a phase separation by nucleation and growth, and of course coagulation of drops by Brownian dynamics, Stokes and Marangoni motion. And of course you have to include the reaction with a monotactic reaction. This is a point which was forgotten in the literature since more than 20 years, that Ferdinand Sommer and Heuer in Chemnitz observed from X-ray scattering and viscosity measurement data that there might be even above the binodal, a few degrees above the binodal, already clusters of the second phase. So this would then always explain why it's not homogeneous nucleation. But it was not followed on. So I hope I could show you that there are links between immiscible alloys and aerogels in the thermodynamics and in the kinetics. And microstructure formation, immiscible alloys has really a lot in common with polymer solvent system. And I have to thank, this would be a long list of colleagues I have to thank, because it was wonderful to work and discuss with them. And this is, I hope you can read it. So? When Hagar, the horrible, discussed with his son, what is the difference between this mountain and this pebble? Well, lack of ambition. So be ambitious. Be ambitious. Okay, thank you.
Lorenz, thank you for making such a complex subject so entertaining. Questions from the floor. We could have, I think, time for a couple if there are any. Yes, we've got one there.
Hi, I'm Basat from Vikas University.
Do you want to take the microphone?
So my name is Basat. I'm from Vikas Brunel University. I have just two questions. One is that have you ever tried to suppress this phase separation by some kind of high cooling rate like splat cooling or suction suckcasting kind of thing?
Also, first of all, for alloys, there's no way to suppress it. You can make, of course, rapid solidification. This was done. The only difference is then you get very tiny droplets. But the phase separation is always there. I do not know of any of the immiscible systems with liquid miscibility gap that you could maybe make an amorphous material. You just get something like 10 nanometers, which was done to study then the effect of curvature on nucleation undercooling.
Another question is that just above the critical temperature, what we have observed for that solids, not the liquid, we observed that there is a very short range ordering we could see. Just above the critical, well, it's still a single phase, but still we could observe using that EXAFS experiments. We could observe a very short range. Have you came across something like that in case of liquid as well?
So I never studied any system close to the critical point. Besides, my colleagues did that for the metastable miscibility gaps, and so copper, cobalt, copper, iron, and they even then always saw droplets appearing, not this famous intermixed two-phase model proposed by Kahn and Hilliard.
Thank you very much. It's really very interesting.
Any other questions from the floor? No? Okay, well, Lorenz,
Thank you.
Thank you so much.